Hello everyone, welcome to the fifth tutorial class on operating system, and it will be presented by myself, Dr. Sudip Mandal. Now coming to the content of this tutorial class, in this class basically we shall discuss a very important topic, that is CPU scheduling or CPU scheduler. So what is CPU scheduler? Basically, in any operating system, many process can move into the ready queue at a certain time. So now to execute all the process, we need to assign CPU one by one. Now how can we assign CPU to each of the process for the execution? That is nothing but the CPU scheduling, and by which we can assign them, that is called as the CPU scheduler. There are lots of algorithms which are already proposed for CPU scheduling problem. We shall discuss one, uh, five of them one by one. Now, before continuing those algorithm, initially we shall discuss some important term those are associated with the scheduling algorithm, like response time, burst time, arrival time, etc., etc. And moreover, we shall also uh, discuss about the Gantt chart, which is very important to understand the operation of the algorithms. Okay, so let's start. So first of all, what is CPU scheduler? I already told that basically the function of CPU scheduler is to select among the process in memory that are ready to queue and allocate the CPU to one of them. Okay, in ready queue there are lots of processes are ready to be executed, but we need to assign CPU to each of them one by one. Most importantly, we should consider here a single processor system. That means we have only one CPU. So how can we assign that CPU to all process for the execution? That is the CPU scheduling, and that is performed by the CPU scheduler. Now whenever a process switch from running to wait state or running to ready state or waiting to ready states or terminate, a CPU scheduling can occur. Okay, now before starting the different algorithms associated with the CPU scheduling, let's let's familiar with some important terms those are associated with the CPU scheduling, like various terms related with the process. Like first of all, arrival time. What is arrival time? Basically, it is the point of time at which a process enter the ready queue. That means if we start the time from 0 second, like a process may enter into 0 second, or a process enter after the 2 second, 3 second, like this. Okay, so at which point of time a process arrival or enter, that is the arrival time. Response time, so basically it is the it is the uh, time that spent between ready state and getting the CPU for the first time. So whenever a process is in ready state or ready queue, after that it may need to be waited to get the CPU. So whenever it getting the CPU for the first time, the time spent between them, that is called the response time. Now waiting time is the total amount of time that is spent by process waiting in the ready queue for getting the CPU. So there is slight difference between response time and waiting time. Here you should consider the total amount of time, but here we should consider uh, getting the CPU for the first time. Okay, so that is the main difference between response time and waiting time. Okay, it is possible that a process may get a CPU for at suppose at 1 millisecond, but after 1 millisecond or after 2 millisecond it may be again moved to the ready queue for the waiting. So in that scenario, uh, response time will be either 1 millisecond, because it is the time to that spent between the ready state and getting the CPU for the first time. But waiting time, it is a total amount time that is spent by a process in the for the waiting purpose in the ready queue for getting the CPU. So that is, this is the waiting time. Now watch time, this is very important, that will be frequently used during the discussion of the algorithms. So watch time is the amount of time required by a particular process for executing the CPU, executing on CPU. So it is also called as the execution time or running time, or commonly also known as the CPU time only. So again, just remember, burst time is the amount of time that is required by a process for executing on CPU. That is called the burst time or execution time. Now completion time. So completion time is the point of time when a process completes and exit from the system. That is the completion time. At which point, like after 20 millisecond, it complete its execution and exit from the OS. So that is the completion time point. Now another important term, turnaround time. Okay, so what is turnaround time? It is the total amount of time spent by a process in the system. That means it's coming to the ready queue, then execute, then move to and exit from the system. So total amount of time that is spent, that is nothing but the turnaround time. So obviously, what is the burst time? Burst time means execution time. So the time spent by the CPU for the execution purpose. So that is the burst time. But before the execution, a process is in waiting state. So obviously, turnaround time equal to burst time plus waiting time. So it should be remembered. Turnaround time is always greater than the burst time or greater than equal to burst time. Okay. So these are the five different um, definition of time that are associated with the process or CPU scheduling. Now CPU scheduling criteria. So whenever we want to uh, propose a particular scheduling algorithm, we should keep in mind that we should always try to maximize the CPU utilization. That means a CPU should be always utilized, maximally utilized. Okay, and maximum throughput. That means we should always try to execute maximum number of process within a certain amount of time. Next, we should always try to minimize the total turnaround time for the process or average turnaround time by the processes. And we should also try to minimize the waiting time. Obviously, it is quite expected that waiting time for a particular process should be minimal, so that a process execute more faster, and we are getting the output or response uh, with more speed. And minimum response time, obviously, so the time taken to get the response, it should be also minimum. So that is the all 5 points should be keep in mind for before the starting of the scheduling. Now another important term, that is Gantt chart. So what is the Gantt chart? Basically, Gantt chart is a project management tool that is proposed by the scientist Gantt initially. It uses basically a simple bar chart, and it is used for the planning and scheduling of the project. Now, in this scheduling algorithms, this Gantt chart is very important for us to understand the operation of the scheduling algorithms. Okay, and these Gantt chart are very useful for simplifying the complex project or complex scheduling problems. Now, we can see different example of Gantt chart in the upcoming slides. Now these are the 5 scheduling algorithms that are already proposed, and these are in your syllabus also. So we will discuss these 5 algorithms one by one. So first one is the first come first served scheduling algorithm. Second one is the shortest job first scheduling algorithm, and third one is the shortest remaining time first algorithm. Fourth one is the priority scheduling algorithm, and fifth one is the round robin scheduling algorithm. Okay, so these are the 5 important algorithms for the CPU schedulings. Now coming to the fast algorithm, that is the fast come fast serve scheduling algorithm, or we can also call it as FCFS algorithm. So as the name suggests, fast come fast serve scheduling algorithm is the simplest scheduling algorithm, and with this scheme, uh, the process that requires the CPU first is allocated the CPU first. Okay, that means the process which come into the ready queue initially, that will get the CPU first. Okay, so here uh, it is quite similar to the FIFO queue, that means fast input fast output. Okay, so the implementation of the FCFS policy is easily managed with the FIFO queue algorithm. Okay, so now consider a real life problem. Here you can see that a process, consider the three process P1, P2 and P3, and those have the burst time 24 millisecond, 3 millisecond and 3 millisecond respectively, and all those are arrive at the ready queue at time 0 millisecond. Okay, so how can we schedule them using FCFS algorithm? So it is quite similar. It is quite simple, that initially P1 will be executed, then P2 will be executed, and then P3 will be executed. Now if we plot using the Gantt chart by using the bar chart, so so it will be starting from here you can start starting from 0 millisecond, and as the continuation of the P1's process is up to 24 milliseconds, so it will be last for 24 millisecond. Now next burst time for the second process is the 3 milliseconds, so obviously the process will last from 24 to 27 millisecond. And P3 process, the burst time for the P3 process is also 3 milliseconds, so it will last from 27 millisecond and end or execute, or it complete its process at 30 millisecond. So you can see that here the waiting time for the P1 process is 0 millisecond, because initially the P1 process get the CPU at 0 millisecond time. Okay, but here you can see that to get the CPU, P2 process need to wait up to 24 millisecond, and to get the CPU for the P3 process, we need P3 process, it need to wait 27 millisecond. So total waiting time for the all process equal to 0 plus 24 plus 27, and if we want to calculate the average waiting time, that is 0 plus 24 plus 27 by 3, that is the 17 millisecond. Okay, so thus we can easily calculate the average waiting time for a particular process or particular problem using the Gantt chart quite easily. Now we want to calculate the average turnaround time. We know that average turnaround time is the total time for the process. That means it consists of burst time plus waiting time. So you can see that to complete the P1 process, we need to wait it complete its 24 millisecond, and you can see that we get the output or P2 process complete at 27 millisecond. Okay, because it need to wait 24 millisecond, and it needs 3 millisecond for the execution purpose. And similarly for the P3 process, it needs to wait up for the 27 millisecond, and it need to 3 millisecond for the execution purpose. So total 30 millisecond is for the P3 process, and total 27 millisecond turnaround time for the P2 process, and total 24 millisecond turnaround time for P1 process. So average turnaround time is equal to 24 plus 27 plus 30 by 3, so that is the 27 millisecond. Okay, now consider another scenario, that if the process, if the order, if the order of the process will be like P2, P3 and P1, so what will be the scenario? Now using the FCFS algorithm, and we can plot the Gantt chart like this. So for the P2 process, it will start at 0 millisecond, and it will last up to 3 millisecond. Next P3 will be executed, that means it will started at 3 millisecond and continued up to 6 millisecond. And the last one is the P1, so you can see that P1 will start at 6 millisecond inter time, and it will be continued up to 3 milliseconds. So here the average waiting time is now for for P1, it needs to wait 0 millisecond. For P2 it needs to wait 0 millisecond, and for P3 it needs to wait 3 milliseconds. So it only 6 plus 3 by 3, that is the 3 millisecond. Okay, so this reduction is quite significant or substantial. So whereas in earlier scenario that is the 17 millisecond, but here we can see that average waiting time is 3 millisecond, and consequently average turnaround time will also reduced, that is 3 plus 6 plus 30, that is the 13 millisecond. So we can conclude that the average waiting time under FCFS policy is generally not minimal, and it may vary quite significantly or substantially if the process of the CPU burst vary greatly. You can see that here that PU burst time for the P1 is 24 millisecond, whereas burst time for the P2 is 3 milliseconds. So there is quite large difference between the burst time between them. So if that scenario occurred, so obviously we get the different type of average waiting time and average turnaround time different depending on the order of the corresponding process. So that is the FCFS algorithm, and their disadvantage also. Now next algorithm is the shortest job first algorithm, SJF algorithm. So as the name just suggests that the in this scenario the first job that will be executed which has the least burst time. Okay, so here in this case this algorithm associate with each process with the each process the length of the latter's next CPU burst. That means we should consider the upcoming burst time, sorry, burst time for the upcoming uh, process. So we need to compare all the process that are coming to the ready queue. So so when the CPU is available, it is assigned to the process that has the smallest next CPU burst. Okay, so we should always compare. That means at a certain amount of time or at a certain time instance, we should compare all the burst time of the processes, and the process which have the least burst time that should be executed first. Okay, now whenever two processes have the same length, same length, so in that case FCFS algorithm will come into the scenario to break the tie. Okay, suppose consider P2 and P3 both have the same burst time. So what will be the shortest job fast scheduling algorithm? So in that case, to break the tie, we need to use fast come fast FCFS algorithm. Fast come fast start. That means the process which have come initially, so that will be selected. Now consider a real life problem, that is consider a there are four process and which have the burst time of 6, 8, 7, 3 millisecond respectively. So if you want to apply the shortest job fast scheduling algorithm for the particular problem, so what will be a Gantt chart? So in that Gantt chart, we know that as per the SJF algorithm, the P4 process has the least amount of burst time, so it will be executed fast. Then P1 will be executed, then P2 will be executed, then P3 will be executed. So as per the shortest job scheduling algorithm, the corresponding Gantt chart will be look like this. That means P4, then P1, then P3, then P2. Okay, so uh, yeah, sorry, yeah. So yeah, so P4 the burst time for the P4 is 3 millisecond, so it will last up to the 3 millisecond. Then P1 will be executed, so as it is has burst time of 6 millisecond, so the turnaround time for P1 is 9 millisecond. And then P3 will be executed because it's at next 7 millisecond, which is greater than the 8 millisecond, so next P3 will be executed. And so you can see that 9 plus 7, that is 16 milliseconds, so it will last up to the 16 millisecond. And P2 will be started at 16 millisecond time, and continuing up to 24 millisecond because its burst time is 8 millisecond. So the waiting time for the P1 is 3 millisecond, waiting time for the P2 is 16 millisecond, and waiting time for the P3 is 9 millisecond, and waiting time for the P4 is 0 milliseconds. So average waiting time is 3 plus 16 plus 9 plus 0 by 4, that is the 7 millisecond only. Whereas if we apply the FCFS scheduling scheme, then the average waiting time will be 10.25 millisecond. We can calculate it. Okay, so you can see that there are lots of difference between the waiting time and the average waiting time between FCFS and SJF algorithm. So you can say that SJF algorithm is the is probably the optimal scheduling algorithm. So it can give the minimum average waiting time for a given set of process. So this is the SGF algorithm, shortest job first algorithm. Now, next algorithm is the shortest remaining time first scheduling algorithm. So you can, as the name suggests, that shortest remaining time first. That means at a particular time instant, we can compare the remaining time of the all the process. So if the process which have the least amount of time for the execution, or least amount of remaining time for the execution, that will be executed first. That is the shortest remaining time first, or SRTF algorithm. Okay, so before starting the SRTF algorithm, let's discuss about the different scheduling algorithm. We can classify basically scheduling algorithm into two types. Basically, we need to discuss this initially. However, we can classify the CPU scheduling algorithm into two types. One is preemptive, and other is non-preemptive. Okay, so preemptive, that means what is preemptive? A preemptive scheduling algorithm will preempt the currently executing process and allow other process for the execution. That means, suppose a current process P1 has been executing. So for the preemptive scheduling algorithm, it is quite possible that the P1 process will be paused, and it will move to the ready queue again, and some other process will be executed first, executed then after that again P1 process will be resume. So if that scenario can happen, that type of process is called the preemptive scheduling algorithm, and SRTF algorithm is such type of algorithm. So why do we call it preemptive? That will be discussed in the upcoming slide. And non-preemptive algorithm, that means it will allow the currently running process to finish its CPU burst. Okay, so the FCFS and SJF algorithm are basically non-preemptive algorithm. So here, whenever a process, a P1 or P2 has been started to execution, it will be completed its CPU burst. Then the CPU will be assigned to the others. But in case of preemptive scheduling algorithm, it is possible that for a certain amount of time, a CPU has been assigned to the P1 process or P2 process, and it is possible that it is moved to the waiting state, and again after completion of others process, it resume its uh, P1 and P2 process. Those are the preemptive scheduling algorithm. SRTF algorithm are the example of preemptive scheduling algorithm. I'm again telling. However, for SRTF algorithm, the process which has the least remaining time will be executed first. Okay, so consider this following example, where we consider four number of processes, and their arrival time has been given as like 0 millisecond, 1 millisecond, 2 millisecond, 3 millisecond respectively. That means P1 has been arrived into the ready queue at 0 millisecond, and at the time CPU is available to us. So obviously P1 will be executed. Then after 1 millisecond P2 has arrived, then after 2 millisecond P3 has been arrived, and P4 has been arrived at after 3 millisecond. And here you can see that the burst time for the P1 is 8 millisecond, and for P2, P3 and P4 are 4, 9 and 5 millisecond respectively. So how can we assign how shortest remaining time first algorithm works for this particular problem? Let's see that. So as we already told that whenever P1 is arrived, at the time CPU is available to us. So you can see that initially P1 is, so there is no other process. So obviously P1 will be initially uh, retain the CPU. So okay, so it will be started, and it will be continued up to 1 millisecond. Now, as after 1 millisecond time, P2 process has been arrived, and you can see that at that time we will compare between what, the remaining time of process P1. So the remaining time for P1 process at 1 millisecond time is 7 millisecond, and the remaining time for the P2 process is 4 millisecond. So obviously uh, the remaining time for the P1 process is larger than the required time for the process P2, so that is 4 millisecond. So process P1 will be paused or preempted, and the process P2 will be started or scheduled. So it will be continued up to 4 millisecond. That means, sorry, it continued up to 5 millisecond, because its burst time is 4 millisecond. Okay. So at similarly, at 2 millisecond time, again we should compare the arrival because P3 will arrive then. Okay, so at that time it will compare. So what will be the remaining time for P3? That means 9 millisecond. And what is the remaining time for the P1? That is 7. And what is the remaining time for the P2 at 2 millisecond is 3 millisecond. So we can see that P2 has the least remaining time, so P2 will be continued. So like this way, so you can see that P2 will be continued for the 5 millisecond, and at 5 millisecond it will be again compared which one have the least remaining time. So you can find that P4 has the least amount of time. So you can see that P4 will be executed. So 5 will be P4 will be executed, and it will be started at 5 millisecond and continued up to 10 millisecond. And like this way, at 10 millisecond again we will compare. So at 10 millisecond we will compare the remaining time of P1 and remaining time of, or total time remain for the P3 time. So for remaining time for the P1 is 7 millisecond, and remaining time for the P3 is 9 millisecond. So obviously P1 will be executed again. So here in this case the process P1 is preempted, but after 10 millisecond it will be again scheduled. This process will be again scheduled, and it will be assigned by the CPU. Okay, and it will be continued up to 17 millisecond, and after that P3 will be started to execute, and it will be continued up to 26 millisecond. Okay, so how can we calculate the waiting time? So here you can see that initially P1 is assigned by P1 process got the CPU at 0 millisecond, but after that it is moved after 1 millisecond. It is again the CPU is assigned to the P2 process, and after 10 millisecond it got again. So the waiting time for P1 process is 10 millisecond. 10 minus 1, that is mean 9 millisecond. And waiting time for the P2 process, you can see that as per Gantt chart, the process has been started at 1 millisecond, but it is has been also arrived at 1 millisecond. So total waiting time, that means 1 minus 1, that is 0. Okay. Similarly, P4 P4 process has been started at 5 millisecond, but the P4 process has been arrived at 3 millisecond time. So total waiting time for the P4 is 5 minus 3. And similarly, P3 process, we need to we need to wait for the 17 millisecond as per Gantt chart, but as the arrival time is at 2 millisecond, so the waiting time waiting time for the P3 process is 17 minus 2, that means 15 millisecond. So total waiting time for the this particular problem is 9 plus 0 plus 15 plus 2, so that is 6.5 millisecond. Okay, so that is the shortest time remaining fast shortest remaining time fast SRTF algorithm. And for the same problem, if we apply the SJF algorithm, we can see that the total average waiting time for this particular problem will be 7.75 millisecond. You can calculate on your own. Okay, so you can see that using this SRTF algorithm, uh, the average waiting time can be minimized further. And we should remember that SRTF algorithm is an example of preemptive algorithm, where a process can be preemptive or paused for a certain amount of time, then again it can be resumed. Okay, now coming to the priority scheduling algorithm, so it is quite simple, and from the title of the algorithm you can easily say that a priority is associated with each of a process. Okay, and based on that priority, the CPU has been assigned to the process. So initially the process which have the highest priority, that should the CPU has been allocated or assigned to the particular process, and after the completion of the that highest priority process, the CPU will be assigned to the next process which have the higher priority. Okay, and similarly, if two processes have the equal priority, so that should be that should be uh, used. The FCFS algorithm should be used in that particular scenario. Okay, now consider this particular problem where you can see that there are five processes with burst time of 10, 1, 2, 1 and 5 milliseconds respectively, and priority are given like this. P1 has the third priority, P2 has the 1, P3 has 4, and P4 has 5, and P5 has that 2. So P2 process has the highest priority, so that means P2 process will be executed initially, and next one is the next one, P5 will be executed, next P1, next P3, next P4. So like this way the process will be executed, and you can see that by using this corresponding algorithm, and that means priority scheduling algorithm, we can plot the Gantt chart for this particular algorithm. So P2 algorithm will be executed for 0 to 1 millisecond because it has burst time of 1 millisecond, and after that P5, that will be executed for 5 millisecond because it has burst time of 5 millisecond, like this way. So after P5, yeah, after P5, P1 will be executed, then P3 and P4. So by using this Gantt chart, and if we can calculate the average waiting time, that will be 8.2 millisecond for this particular problem. So that is the priority scheduling problem. So now the problem is how can we decide the corresponding priorities of particular process. So priorities can be defined or selected or calculated by internally or externally. So internal priority can be defined by some measurable quantity like time limit, memory requirement, the number of open file, the ratio of average IO burst to average CPU burst, lots of things like this. So that means the process which have the least amount of time requirement, that have the higher priority. So like this way internal priority can be calculated, whereas external priority are set by the corresponding user, and these are the set by the criteria that are external to the operating system, such as the importation of the particular process. So these are the internal priorities and external priorities that should be keep in mind during this application of the priority scheduling algorithm. Now coming to the last scheduling algorithm, that is the round robin algorithm, round robin scheduling algorithm, or RR scheduling algorithm. So basically this is quite similar to the uh, time division multiplexing. You already know in the analog communication or digital communication that we can say we can send or transmit multiple number of signal at certain time interval one by one. Okay, so same scenario or same concept has been used in case of round robin scheduling algorithm, and we should also keep in mind that this type of algorithm is designed only for the time sharing system. So here we know that in case of time sharing system, multiple system, that means resources are shared by the defined user for a certain amount of time frame. Okay, so in that scenario round robin scheduling algorithm can be used. So here we are considering a small unit of time that is called the quantum time or time slice. Basically it is around 10 to 100 millisecond amount of time, and this amount of time is used to switch between the particular process. Okay, so whenever there are multiple number of process in the queue, so for particular time frame, sorry, particular time slice or quantum amount of time, quantum time, each of the process will be executed, and again it will move to the ready queue, and after that time frame or time slice, others process will be executed, and after completion of the others quantum time, again the process will be resumed. Okay, so the CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval up to one time quantum. Okay, so consider this particular process, particular example, like P1, P2 and P3 process, and whose burst time are 24, 3 and 3 millisecond respectively, and all the process has been arrived at the ready queue at time 0 millisecond time of 0 millisecond time. So how can we apply RR scheduling algorithm for this particular problem? Remember, RR algorithm is also example of preemptive algorithm. That means here a process can be preempt or paused for a certain amount of time, and it will be moved into the ready queue, and after certain amount of time this execution of that particular process will be again resumed. Okay, so that's why we called it as the preemptive scheduling algorithm. Round robin scheduling algorithm is such type of algorithm. Now let's see how this problem can be solved. So consider we can consider here a time quantum of 4 millisecond of time. That means time slice is equal to 4 millisecond. That means for any process, uh, each the process execution time will be 4 millisecond, and after that the process will move into the ready queue, and next process will be executed. So again, after another time quantum or time slice, that process will be executed, and after that next process will be executed. Like this way it will be continued until unless all the process all the process is completed. Okay, so you can see that if you use a time quantum of 4 millisecond of time, then process P1 will get the first 4 millisecond of time. You can see that the total burst time required for the P1 is 24 millisecond. So remaining time for the P1 process will be 20 millisecond. But as we are using RR algorithm, that means uh, P1 process will be executed for the one time instance only, one time slice only. So initially P1 will be executed for 4 millisecond. Next P2 will be executed. Now burst time for the P2 process is 3 millisecond. So we don't require full time slice of the process. Time slice. That means it will be last up to only 3 millisecond. That means it will be continued from 4 millisecond to 7 millisecond. And similarly, P3 process. Similarly, for P3 process, after that, after the completion of P2 process, P3 will be continued or P3 will be started. So at 7 millisecond, P3 will be started, and for the same reason as the time burst for the or CPU burst time for the P3 process is 3 millisecond only. So we don't require full time slice or quantum time, that is 4 millisecond. So P3 process has been started at 7 millisecond, and it will be started up to 10 millisecond. And after 10 millisecond, again P1 process will be continued. Okay, so you can see that after 10 millisecond, the next time slice is for 4 millisecond, 4 millisecond, 4 millisecond, 4 millisecond, 4 millisecond. So P1 will be executed for 4 millisecond initially. Now as the P2 and P3 process has been completed, so there are no process in the queue. So then P1 will be executed for next 4 millisecond, and again P1 will be executed next time slice, next time slice, next time slice. So total amount of time for the P1 process is 24 millisecond will be computed by this amount of time. Okay, so the resulting Gantt chart will be look like this. Okay, so waiting time for the P1 is, you can see that uh, P1 has been started at 0 millisecond, but next for the next process, but next after P2 and P3 process, P1 again resumed. So we can say that the waiting time for the P1 is the 10 minus 4, that is 6 millisecond. Okay, and for P2 process you can see that the waiting time is 4 millisecond, and P3 process the waiting time is 7 millisecond. So the average waiting time is 17 by 3, that is 5.6 millisecond. Okay, so you can see that by this is quite similar to the time division multiplexing. Okay, where initially one user or one signal has been transmitted for a particular time slot. In the next time slot, second user. In the third time slot, next user, like this way. So here we can also see that in case of Robinson, round robin scheduling algorithm, initially for each initially each process has been assigned by the CPU for a particular one time slice only. Okay, so in the RR scheduling algorithm, no process is allocated the CPU for more than one time quantum in a row. So you can see that uh, if there are many processes are in ready queue, so in that scenario, no process is allocated the CPU for more than one time quantum. So here you can see that P1 is allocated for one time quantum, then P2, then P3. Okay, and it will be repeated until unless all the bus time is completed. As at this point there are no process other than P1, so that's why P1 is P1 is assigned by the CPU serially or in a row. But if at this point there is P2 and P3 process, so after that it should be P2, next that should be P3, like this way it will be continued. So coming to the conclusion part, so in this class we have studied different basically CPU scheduling algorithm like FCFS, SJF, SRTF, priority scheduling, round robin scheduling algorithm. All these algorithms are associated with the CPU scheduling, where uh, we assigned the CPU to particular process whenever there are many processes in the ready queue. Okay, so, and we also discussed different term associated with the CPU scheduling, like arrival time, burst time, waiting time, turnaround time, etc. And we have also familiarized with the Gantt chart. Using Gantt chart, we can easily analyze the scheduling problem. Okay, so these are the references. If you have any problem, please post them. Thank you.